Hi everybody, hope all of you are doing well and been having a great time. Now this time me Nasser presenting operating system security patch management plus vulnerability management. The remainder of this presentation is organized as this outline: abstract, introduction, overall paper discussion on the topic, literature review, challenges, future works and remarks. Many software programs are built on a regular basis all over the world, but they often include flaws and vulnerabilities as a result of poor design methods or implementation strategies employed by developers. Hackers take advantage of these vulnerabilities to further their malicious purposes. The timely application of software updates and patches, particularly in the context of end-user apps, is inextricably linked to effective vulnerability management. In order to solve this issue, only timely patching of an operating system's intended vulnerability will secure our information systems from a malware attack. Now moving on patch management and vulnerability management. What is patch management and vulnerability management? Patch management is a logical process for upgrading software, operating systems and programs on an asset. A patch management system's goal is to identify, classify and prioritize any missing patches on a given asset. Patches fix security and functionality issue with software and firmware, and they are typically the most powerful way to mitigate software vulnerabilities. If not, upgrades can only fix security and functionality issues with previous software and firmware versions. And vulnerability management is a process that identifies assets on network, classifies the assets, operating systems and programs, and generates reports on security vulnerabilities on target systems. The cyclical practice of identifying, classifying, prioritizing, remediating, and mitigating software vulnerabilities is known as vulnerability management. Vulnerability management should not be confused with vulnerability assessment when it comes to computer and network security. Patch management and vulnerability management are not products; they are processes, and the products are the tools that enables the process. Vulnerability detection and patch management are often combined and confused to be at the same time. They are not the same even if they have a compatible relationship. Vulnerability and patch detection are two distinct types of process that are used to facilitate these systems. They have different purposes and goals. Vulnerability management typically resides in security operations, while patch management sits in operations. So overall description of the topic is vulnerability analysis and patch management using secure mobile agents, security, vulnerability and patch management in electric utilities, a data-driven analysis, automatic patch-based exploit generation is possible, techniques and implications introduction, an empirical analysis of software vendors, patch release behavior, impact of vulnerability disclosure. Before we knew it, an empirical study of zero-day attacks in the real world. Vulnerability management, not a patch on where we should be. NIST, procedure for handling security patches. SANS, framework for building a comprehensive enterprise security patch management program. From all these perspectives, this paper presents a comprehensive analysis of patch management versus vulnerability management. The time aspect of operating system patching was the key subject of the entire research survey. Many software programs are created on a regular basis all over the world, but they often include bugs and weaknesses because of bad design methods of implementation technique employed by developers. Hackers take advantage of these bugs to further their sinister aims. To address this problem, the writers built and implemented a framework for systematic vulnerability detection and patch management. Their device gathers the latest up-to-date details regarding vulnerabilities on its own, analyzes hosts in the local network for possible vulnerabilities, and implements necessary fixes on its own. The findings of their testing indicate a substantial reduction in intrusions while also improving network management for device administrators. Many software systems have a significant number of discovered bugs according to NIST statistics as seen in Figure 1. MagicNet system comprises 5 major components: comprehensive vulnerabilities database, database management engine, MagicNet vulnerability management console, mobile agent, and sensors. Figure 2 depicts a description of the structure and the components interactions. This architecture demonstrates that with this technology, a security administrator may significantly reduce the amount of time it takes to manually search all hosts on the network for bugs and install patches. For electric utilities, security vulnerabilities are a significant concern. Vulnerability data analysis has gotten a lot of coverage, but vulnerability and patch management in electric utility has gotten a lot less. Unlike the others, the research examined a real vulnerability and patch management dataset from an electric utility to shed light on current practice. The dataset includes not only vulnerability records but also details about how vulnerabilities are treated in operation. This paper examines the statistical characteristics of such vulnerabilities in terms of software, assets, and other metrics, as well as how vulnerability characteristics influence human operators' decision about patching and implementing mitigation plans. Based on the dataset, the author investigates statistical characteristics of vulnerabilities as figure 1, 2, 3 are the sum of the concerns that need to be answered. How are software vulnerabilities distributed? What is the vulnerability distribution and exploitability across assets? What is the distribution of the CVSS score across assets? The effects of exploitability on remediation decisions are visualized in figure 4. Figure 5 illustrates the influence of attack vector on remediation decisions. The distribution of vulnerabilities through software and asset is skewed, indicating that the bulk of vulnerabilities are contained in a small subset of software and assets. Furthermore, exploitability and attack vector are two significant considerations that influence vulnerability remediation decisions. At first glance, releasing a patch to fix security vulnerability appears to be a win-win situation. However, when it comes to patch distribution, we must consider the entire time frame. A new patch reveals some information. An attacker may benefit from early access to a patch. From a security perspective, we should think about what information a patch reveals about a previously unknown vulnerability, how easily that information can be retrieved from the original and patched software, and what benefit that information gives attackers. The researchers demonstrate that automatic patch-based exploit generation, that is APEG, is feasible based on their experiments with 5 recently patched Windows programs. The APEG program is given a program P and a patch version of the program P bar automatically generate an exploit to the potentially unknown vulnerability present in P but fixed in P bar. In the point of input validation vulnerabilities, in which the set of inputs accepted by P is a superset of the safe inputs for P. Figure 1 visualizes the intuition where the set of safe inputs is a subset of all P inputs. The difference between the safe and all inputs accepted by P is the set of exploit inputs. Adding additional input sanitization checks to P bar to ensure that only safe inputs are processed without error is a common approach for patching such vulnerabilities. Buffer overflow, integer overflow and underflow, and heap overflow are among the most specific examples of input validation vulnerabilities. Figure 2 illustrates a typical integer overflow input validation vulnerability that we use the writer used in this paper. This example is based on a real-world Internet Explorer vulnerability. If APG is effective, it will show that attackers can build vulnerabilities using patches. In their research, they were able to produce an exploit automatically utilizing just the unpatched and patched software in a matter of minutes. They developed innovative methods for evaluating possible exploitable pathway to a new sanitization check in order to obtain their performance. Since better protection and standards require that they conservatively measure an attacker's capacity, their findings suggest that automated patch-based exploit generation should be considered realistic in security-critical scenarios. The timely release of patches by software vendors for vulnerabilities in their system is an essential feature of improved and more secure software. The writer collected details on when the vendor was alerted, whether and when a fix was made available, whether and when the vulnerability was publicly revealed, the extent and seriousness of the vulnerability, and vendor characteristics for each vulnerability vendor pair. The findings of the systematic empirical investigation suggest that patch release is accelerated as information is made public. Because of the disclosure, the chance of launching the patch increases by about 2.5 times. Open source vendors release updates quicker than closed source vendors. As seen in graph, vendors respond rapidly to more serious vulnerabilities. They have also learned that vendors are slower to react to bugs that haven't been revealed by CERT, that means the Computer Emergency Response Team. This is most likely due to a better cooperation between CERT and vendors. The importance of CERT's vulnerability analysis and therefore CERT's credibility. They double-check their findings with a publicly accessible dataset and find that the results are consistent. They also illustrate how their predictions will help policymakers make better decisions. They used a one type of data set to build a proportional threat model of patch release times. To put it another way, as opposed to no exposure, instantaneous disclosure forces a vendor to issue a patch 35 days sooner. Before moving on to the calculations, figure 1 shows that Kaplan and Mayer approximation of the survival function or the likelihood of survival over period with and without disclosure. Figure 1 indicates that the risk of a patch release is greater with publicly reported vulnerabilities. If a vulnerability has been disclosed, almost 75% of the vulnerabilities have been fixed by within day 50, although less than half have been patched if no disclosure has occurred. Now we'll look at zero-day attacks. While zero-day attacks have been debated for decades, little research has yet been done to determine the duration and prevalence of these attacks in the modern world until the vulnerabilities are publicly disclosed. So in this study, the writers took a step in the right direction by studying field data generated over a 4-year span on 11 million Windows hosts. The study main goal is to find executable files that are connected to established vulnerability exploits. They systematically detected zero-day attacks and studied their evolution over time by looking for these files in a dataset of historical records of files downloaded on int hosts around the world. A zero-day attack is one that takes advantage of vulnerabilities that have not yet been publicly revealed. As seen in figure 1, this is just one phase in the life cycle of these vulnerabilities. Figure 2 represents the events that mark during this life cycle. They found 18 vulnerabilities that were exploited in the wild before they were officially revealed, 11 of which were previously unknown to have been used in zero-day attacks. Zero-day attacks usually last 312 days, but can last up to 30 months, and they only impact a few hosts. There are several exceptions, such as high-profile attacks like Configure, exploiting zero-day Configure. Zero-day vulnerabilities rises by up to 5 orders of magnitude once they are made public. The timely application of software updates and patches is inextricably linked to successful vulnerability management, especially in the context of Windows applications. Vulnerabilities continue to be found often in well-established applications, necessitating the writer's constant focus. Figure shows the findings of a survey of 290 users they undertook as part of wider security literacy research at Plymouth University, which show their lack of timeliness in implementing updates. Although it can be seen that a small majority claim to follow best practices, such as installing updates as soon as they are available, which in some cases is bound to be aided by the use of automated features, or if they are flagged as critical, which is typically the case for those affecting security, and almost equal proportion express a concern that their systems will not be adequately protected. While a minority of these openly claim to ignore updates, those who claim to install at some stage cannot be considered good practice because the time it takes for this point to arrive is highly dependent on how long it takes. Although they are represented in figure 1 as a general concept, updates in reality will take several forms. In some situations, this involves patching outdated application, and in others, it entails upgrading to a different edition entirely. The condition is a little improved on mobile devices, which have effectively equipped them with a different background in which to face challenges. According to research published by Duo Labs in early 2016, 90% of active Android devices are running out of date operating systems. The adoption of iOS on the Apple side, on the other hand, seems to be better. For example, it was reported that 3/4 of active iOS devices had iOS 9 installed only 4 months after its release. In the survey, I looked at pest management methodologies from a variety of mainstream organizations, including NIST and SANS ACSC. In this section, I will discuss some of the findings. NIST recommended creating a skill patch and vulnerability group, that is PVG, in order to assess an organization's vulnerability, threats, and risk. A system administrator leads the PVG. The following points explain the summary effects of NIST suggested patch management procedure. First, creating PVG. Implement patch management tools that are automated in your organizations. Evaluate and mitigate the risk of a newly discovered vulnerability and its patches. When configuring the operating system, stick to a standard framework and avoid the auto configuration option. Follow up on the patch management procedure and program on a regular basis, and continually improve the overall patch management process by correcting errors. On a regular basis, conduct PVG training and awareness programs. Now we'll look at a typical patch lifecycle proposed by SANS Institute, and I have seen how PVG interacts with each phases of the life cycle. Now moving on, challenges, future works, and remarks. For the MagicNet framework to achieve its maximum capacity, a variety of problems do need to be overcome. The patching system is without a doubt one of the most crucial. The framework distributes updates and will only load those that do not need human interference, such as Windows executable file with no parameters. Future research would be performed to see whether it is feasible to deliver the input request to the system administrator whenever it is necessary during the implementation phase utilizing mobile agents, and then submit the responses back to the target host. Such activities could save time for administrators and could be executed autonomously on the other host without the need for interference from administrators. Their model does not account for patch quality in the area of empirical analysis of software vendors' patch release behavior. Additional resources allotted to patch management can result in a higher quality patch than released sooner. They examine the effect of actual disclosure on vendor conduct rather than the threat of disclosure. Policymakers and vendors would benefit greatly from future research that can determine the effect of a real exposure from the threat of disclosure. They indicated that existing patch delivery systems are insecure and could be revamped to more thoroughly protect against automatic patch-based exploit generation. In the paper of automatic patch-based exploit generation is feasible. Additional analysis is required to measure these aspects of the full disclosure trade-off, such as evaluating how rapidly insecure hosts are patched in the field after vulnerability disclosure. As outlined in empirical study of zero-day attacks in the real world, answering these additional research questions, including their analysis of zero-day attacks, would involve large-scale empirical experiments focused on detailed field data. Not all patches provide security updates, and not all updates will solve the challenges identified. Therefore, using a patch management tool is not enough to keep us secure. Patching operation system is not enough. Vulnerability management should be there. These are the overall references of the overall paper description of the topic. So that's the end of my today's presentation. Thank you.